Hello. Oops. Where am I? Okay. I'll be using an example of DC shunt motor to demonstrate the nonlinearity on DC machines. This is basically a DC motor without compensating windings. You have this in your slides. The output power is 50 horsepower with an input of 250 volts. That's basically the voltage at the terminals. The no load rated RPM is 1200 with armature resistance of 0.06, field resistance, shunt field resistance of 50 ohms. This is 0.06 ohms. The number of turns per pole in the field is 1200. So you have an electromagnet with 1200 turns per pole. Then later on we'll be introducing an armature reaction of 840 ampere turns. I think I mentioned armature reaction before. So yeah, in this video also I'll be demonstrating the effect of the armature reaction, the formation of a magnetic field in the armature. So what's required is the speed of the machine, of the motor. What's the speed of the motor at 200 amperes? Take note, this speed, which is 1200 RPM, is just the rated no load speed. Okay, so if the line current is 200 amperes, so this is what your DC shunt motor will look like. So if your line is 200 amperes, this one, take note of the direction of the current. The current goes into the machine. So you have the terminals here, 250 volts. The line is 200 amperes. The 50 horsepower. The 50 horsepower is here. But of course, that is after you subtract the mechanical power, because the power here is the power developed at the armature. So you subtract the mechanical power, that's 50 horsepower. Okay, so the direction of the current is that you have this 200 amperes going into the machine, this field current in the shunt field going down from positive to negative, because the voltage here would be positive here, negative here to 50 volts, and the armature current that's going into the armature. Yeah, okay. So for the field current, sorry, wait lang. For the field current, that current would be 250 volts to 250 volts here divided by the 50 ohms here, so it's 5 amperes going down. So if you perform KCL in this node, we can get the armature current as 195 amperes. So the armature voltage, the voltage at the armature would be 250 volts, the voltage here by KVL, less this voltage drop of 195 times 0.06. Yeah, so it's 238. We don't have the voltage at the brushes here, so I guess let's assume that voltage is negligible, or probably it's incorporated in this 0.06 ohms. But yeah, I think, yeah. Anyways, okay, so the voltage developed at the armature is 238.3 volts. Okay, now I want you to remember this because we'll be using this value a lot. What does 1200 RPM no load mean? So it just tells you that if you are running at no load, then that is this no load. If we are running at no load, therefore the output power is 0. Well, let's assume well, this will not this will not be, what do you call this, this will not be true, but I think, yeah, let's assume that this is very very small. Okay, well, the output power is 0, so let's assume that this is very very small, such that it is equal to 0, such that this EA will be close to 250. I guess that's let's just say that we want to use that approximation to simplify the problem. Okay, so you have the induced voltage of the armature of 250 volts, and that results to 1200 rpm. That is at no load. So that just tells you that, okay, if we are not, if the motor is not loaded, then it is running at 1200 rpm. Of course, your power output is torque omega. So if this is 0, it doesn't necessarily mean that the omega is 0. It just tells you that you have torque of 0. Okay, okay, so now take note that the voltage induced at the armature is equal to Ponzi over 60A, where your poles, number of conductors, 60 and A are constant. So instead of using Ponzi over 60A, we can just make those constants as K, and then relate EA into the magnetic flux and the speed of rotation. So if at no load we are running at 1200 rpm, that is when the voltage at the armature is 250. So we can use that relationship to get the speed of rotation if EA is 238.3, because we need that by KVL. EA is 238.3 when the line current is 200, then EA is 238.3 by KVL. So we can use that relationship, to that econ relationship, to solve for N. How about flux? Well, flux when EA is 250 is just the same flux when EA is 238.3, because you have the same machine, therefore the same construction, and you have the same field current. It's 5 amperes here, it's 5 amperes here. So you have the same field current, therefore you produce the same flux. So if you use that relationship, you can cancel this K, you can cancel this phi, then solve for N. So N is 1143.84. So as you can see, if you can still remember our formula for speed regulation, it's no load minus full load all over full load. Our no load speed, which is 1200, is greater than our loaded speed, which is 1143. How do we know that it's loaded? Well, you are getting line current of 200 here. 5 of that goes to the field. The remaining will go to the mechanical losses and the output power. Okay, so yeah, that's basically how you use that formula. It's a linear relationship. Now take note that this topic is intended to show the nonlinearity of DC machines. So yeah, well, I haven't showed that yet. So this is how you use that equation. It's basically linear. How about the effect of armature reaction on the field? So take note that the field current is 5 amperes. So if you can still, if we go back here at the given, we have 1200 turns per pole on the field. Therefore, the MMF at the field is 6000 ampere turns. It's just 5 amperes times 1200 ampere turns per, that's per pole. Now your armature reaction kind of opposes the magnetic field the 6,000 ampere turns, reducing the total flux so experienced by the machine. So if we have a total of 6,000 per pole and an armature reaction of 840 ampere turns, then the effective MMF is 5,160 ampere turns. And yeah, we can use this relationship again, econ, to get the new speed. So in this scenario, instead of canceling phi and k, we'll just be able to cancel k, because we have a value of phi, which is 6,000 over reluctance, and 5,160 over reluctance. So what does this formula give you? This tells you that if I want the same voltage at the armature, the same 238.3 at the armature, I should have 1,330 because of the effect of the armature reaction. Otherwise, if I have an effect, if I have if I use the same RPM and introduce the armature reaction of 840 such that I only have 5,160 in the effective field, probably I'll be getting less than 238, and we don't want that, because if we perform KVL, we'll probably end up with a lower voltage here, or well, it will affect the electrical performance of the machine. Yes, so you want to have this 238.3 here. That's why you want it to run higher, to run faster, because of the lower magnetic field. So yeah, that's basically the effect of armature reaction. Now, from the no-load characteristics, we know that you have the flux 6,000 ampere turns. Well, yeah. Without the armature reaction, we know that the flux is 6,000 ampere turns divided by the reluctance of the machine, and the speed is 1,200. And when you have this much flux and this much speed, you are producing 250 volts. If we apply an armature reaction of 840 ampere turns, then for the same speed of 1,200, instead of getting 250, we'll only be getting 215. Now that's the linear relationship of the voltage and the flux, assuming that we are running at the same speed. If we are running at the same speed, then we can produce this linear relationship of induced voltage and magnetic flux. However, we have this saturation curve, and I think I was able to mention this in the previous video on DC generators. Yeah. Is it? Yeah. It's in that video, or DC motors. I'm not sure. Okay, that the saturation curve describes the saturation of the core. So what does it mean? It just tells you that your core tends to fill up with flux, such that it comes to a point where it can no longer accommodate any more flux. So because of this, so the thing here is that if you have a field current, as you increase the field current, the armature, the induced voltage, tends to increase. However, it comes to a point where the change in armature voltage is no longer is decreasing with respect to the change in the field current, in the strength of the magnetic field, such that when the core is fully saturated, even though you increase further the field current, you no longer have an increase in the armature. So that's the nonlinearity of the field, of the DC machine. Yes. If we consider this saturation curve, this saturation curve tells you that if the field current is 5 amperes, you get an open circuit voltage at the induced voltage of 250. If it is 4.3 amperes, you get 233 volts. Okay, so that's how you interpret the saturation curve. Now let's apply the armature reaction of 840. If you apply 840 armature reaction ampere turns, then the effective MMF would be 5160 ampere turns, or the effective field current is 5160 divided by 1200 turns, or 4.3 amperes. So what happens here is that though I have 5 amperes here in the field, because of the armature reaction, the effective field current is 4.3. How about the computation of the what do you call this? How about the computation of the power loss on the field? Will I use 5 amperes for I squared R, or will I use 4.3 in I squared R? Well, we'll be using 5 amperes because technically that is still 250 over 5. This 4.3 is just because you want to represent that counter magnetic field in terms of current. So instead of using 5, you have 4.3. And using the saturation curve, at 4.3 amperes, the induced voltage at the armature is 233 and not 215, as opposed to this one. So from the original problem, if you want 233, from the original problem, the armature voltage is 238.3. So if you want 238.3, from 233, that is derived if you have flux of 5160 all over reluctance times 1200 RPM, because this characteristics, this saturation curve is when N is 1200 RPM, is equal to, you get this relationship, then you get this, you can cancel that, and then you get the new speed, which is 1227. So if you want 238.3, you want to run your machine at 1227 RPM instead of just 1200, because if you run that at 1200, you'll just get 233. So that's basically the nonlinearity of the DC machine. You have nonlinear reaction because of the saturation of the core. So you cannot make the field current infinite to make the voltage at the armature infinite. So there is a point there where you can no longer increase the induced voltage at the armature, because the core can no longer admit that much flux, because it is already saturated. Okay, so I guess that's nonlinearity of DC machines. So yeah, Stay safe.